Welcome to Organic Chemistry 2. This is day 1. So let's talk about Organic Chemistry 2 today, and we'll start on Chapter 10. But before we get started, I want to make sure that you spend some time today checking out Blackboard. And in Blackboard, you need to check out the syllabus and the course calendar. You should see dates for when things are due, like online quizzes, in-class exams, online homework. In the syllabus, you should look at your point values and see. So you'll need to read all that on your own and then bring questions face to face, or you can email me questions as you see. I would like to, so go ahead and take this time to get on your online homework and start the online homework. You might have some review for Organic Chemistry 1. You will have an ACS exam, a national exam for your final in here, so you can see how many points that is. And both classes will be taking that exam. So look at the calendar and make sure you have that on your calendar in May. That exam is 70 questions. It's a national exam, and half of those questions, so 35 of them, will come from Organic Chemistry 1 material. So I will try to incorporate Organic Chemistry 1 reactions in a lot of your synthesis. So we'll talk about synthesis in Chapter 11, and you'll always have some synthesis questions on your exams, and you'll have to be responsible for your Organic Chemistry 1 material. Same thing with nomenclature. You always have nomenclature on your exams, and that would include Organic Chemistry 1 or intermolecular forces. Okay, so I am Dr. Thomas. This is me, Dr. Thomas. Okay, this is my family. This is my husband, Mark, and he has a PhD in biology. This is my daughter, Sarah, and she is a sophomore at University of Washington, and she's a pole vaulter. My other daughter is my stepdaughter, Mary, and she's at EKU. She's a senior this year, and she got accepted over the break in physical therapy school at UK, so we're excited about that. Paul is my stepson, and he is driving, and he's in high school. And this is Sarah's boyfriend, Nathan Green, and he is the NCAA 1500 meter champion from last year. He's from Idaho. So that is me. I grew up in Northern Kentucky, Carrollton. I want you to do this on a piece of paper, print your name, and tell me a little bit about you and where you grew up. I'll add 2-point bonus onto your exam 1. So I got a bachelor's degree at UK, and I decided I wanted to do chemistry. I wanted to actually do cancer research. I wanted to actually synthesize a cancer drug. And so I had to get my master's degree in organic chemistry to learn how to do that. And then I spent 6 years working at Eli Lilly. Those were great years. I loved research, making new compounds pretty much every day. But then Sarah was born, and I went into teaching. And so in order to teach, I needed to get my PhD. So got it at the University of Kentucky. Little things about me: I ran the Boston Marathon in 2006, and maybe I'd like an interesting fact about you. It helps me get to know you better. All right, so today's agenda, like I said, look over the syllabus, take your time, read that, see how that's broken up. Look at the different activities, look at your course calendar. I will have these available for you when you're in class with your folder. We'll have groups of 3 people each in a group, and you will have a group folder. I want you to make sure you can draw organic structures. I want you to review some organic 1 problems, and we'll kind of incorporate these things, but we're going to start chapter 10, radical reactions, today. Okay, so here's a question. Which of the following is not a reasonable Lewis structure? So if you remember, carbon, so we're talking no formal charge, right? Carbon, this is my heart, loves 4 bonds, right? 0 lone pairs. What else do we know? Hydrogen does single bonds, 0 lone pairs. Fluorine does single bonds with 3 lone pairs. So fluorine and hydrogen always have to be terminal. They cannot be in the middle. Boron loves 3 bonds, 0 lone pairs. So it is an exception to the octet rule. Oxygen loves 2 bonds, 2 lone pairs. And these are your typical elements that you find in organic chemistry. We do nitrogen. Nitrogen loves 3 bonds, 1 lone pair. Now what happens if you find an element that isn't going with these bonding patterns? Okay, then you need formal charge. And you remember formal charge equals the group number minus dots minus dashes, right? And so it needs a formal charge if it does not obey these bonding patterns. So here's nitrogen. It has 3 bonds, 3 lone pairs. What's the functional group? Also review functional groups. This is an amine. Here we have oxygen with 2 bonds and 2 lone pairs, right? So that's good, right? And what is this? This is an alcohol. Here we have fluorine in the middle. This is not okay. Okay, so C would definitely be not a reasonable structure. Fluorine has to be terminal. Here we have alkane, and so this is ethane. And here we have a boron, which is fine. So you see how you can incorporate review, formal charges, bonding pattern, Lewis structures. All right, what is the formal charge of the nitrogen atom in the following structure? Okay, so 1, nitrogen has to obey the octet rule. So in your second row of the periodic table, you cannot, no element cannot exceed the octet rule. So it's not an okay structure if it has more than 8 electrons. Okay, so it can't have more. So oxygen looks good, hydrogen, this is a carbon, right? So formal charge for nitrogen equals, what's its group number? 5 minus dots, well there's 0 dots, no lone pairs, minus dashes. 1, 2, 3, 4. So 5 minus 0 minus 4 is a plus 1. So that's just a review of formal charge. And you'll see that on your ACS exam, Organic 1. All right, so we're going to do radical reactions. You want to be able to say, I can determine the major organic product and 3 types of free radical reactions. So we're going to, and you want to draw the reaction mechanisms. So this is your chapter 10 goal. All right, so this is review. This is an alkene. You see the functional group? Here's your alkene. And so you're adding HBr. And so this is review. And the mechanism is electrophilic addition. Right? Do you remember that? EA. And so H adds to one of the carbons and Br adds to the other of the carbon-carbon double bond. So one of these is going to get the H and the other one's going to get the Br. Well, this is a strong acid, right? And so these electrons here are going to go and get the electrons from H, and then those electrons are going to go to the Br. You see how this is a mechanism when I showed the movement of the curved arrows. Now I got to show the intermediate there. We're not touching the aromatic ring, okay? We're not there. All right, so we still have this sigma bond here, but H is going to go there, and the plus goes there. There's your intermediate. So we get an intermediate carbocation, and this follows Markovnikov's rule to give us the more stable carbocation. And then we have the bromine that took the electrons, right? And then this is going to come in and add there, and we can find this is our product right here, where the Br adds to the benzylic position. This is called the benzylic position, and this is electrophilic addition. Now this is new. The mechanism is new. It is review, though. If you remember, this is the anti-Mark product when we did electrophilic addition, and that's because this has the thing we called ROR, and so this is a peroxide. So what happened was the scientist used an old bottle of HBr and got the anti-Mark product, and kept doing that and kept doing that, and the PI, which is like the boss, kept saying wrong, wrong, can't be, this can't be. He's like, boss, this is happening. And so then they purchased a new bottle of HBr, and they didn't see that. It went Markovnikov edition. Okay? So it turns out that a new mechanism was discovered. And this is a free radical mechanism. So we're going to learn that new mechanism this chapter. So here, I'm not going to do the mechanism like we did before, because that's not the mechanism. But you are going to be responsible for this mechanism now. And what happens is peroxides, the oxygen-oxygen bond is really weak, and it can split. And it does a thing called homolytic cleavage. And that means one electron of this bond goes onto the oxygen, and another electron goes on the other oxygen. This is called initiation. So you have an initiation step, and this is it, and it gives you two free radicals. Okay, and so then that free radical then will react with HBr. This is still the initiation step. Sometimes people just write I, and this one electron will go and take away the hydrogen, just like that. Notice these are fish hook arrows. They're half arrows because it's a movement of one electron only. So then you get that plus the Br radical. So now this is in your flask. This is happening before it ever, or in your bottle of OHBr, before you add your alkene. Now when you have your alkene, then you have a thing called propagation. So you can have, and this is your first step. Step 1, propagation step. You take this free radical that was generated and you react it with your starting material. And now we have the Br, and the Br is going to add to that carbon. One of the electrons go there, one goes there. So you see you have 3 fish hook arrows. And then this becomes your intermediate product, okay? So you notice that free radicals. We'll talk about free radicals in this chapter, but they follow the same stability pattern as the carbocations. Okay, that is big deal. Okay, so if you have a secondary carbocation, that's more stable than a primary, just like a secondary free radical is more stable than a primary. So it follows the same pattern, and there's no rearrangement. So you don't have to worry about hydride shifts, okay? All right, so that's propagation step 2, and a lot of times you do P2 for propagation step 2. So that's propagation step 1. You have to take this free radical, that's the start, and now you have to react that with another HBr. We're going to have 3 fish hook arrows here, and then that's going to give you your product, which is D, because the H will go here. So that's D, and you see that's the anti-mark product. So just like if you had the mark product with HBr, that would give you this intermediate, and you would get this product, which would be B, product B. So that's the mark product, this is the anti. Okay, so we're going to focus on 3 reactions. This gives you the anti-mark reaction. You see the peroxide, so this generates, well, you need to know the mechanism. This generates the free radical that reacts with HBr, and then you have the alcohol and then the Br radical. And now the Br radical can go into propagation steps 1 and propagation steps 2 to give you the anti-mark product. The other radical reactions we're going to focus on is allylic bromination. So we'll talk about N-bromosuccimide, which N-bromosuccimide looks like this. And it's a source of low concentration of bromine radicals. It's a white solid, and usually just H nu is energy equals H nu, which is a photon light. So you can shine the light to generate that free radical. And this is allylic, so it will actually brominate on allylic position. So you need to recognize that when you have this double bond here, this is sp2, sp2, and then this is an sp3 carbon. And the reason why this works is because this hydrogen here, when bromine actually abstracts it, you get this free radical, and that free radical is stabilized by resonance. So that makes, because of the stability of the resonance stability, allylic, that hydrogen there is easy to abstract. Okay, so we're talking about abstracting a hydrogen, and that abstraction of that hydrogen has a low BDE, which if you look up BDE, that's bond dissociation energy. And that means it's low energy to remove it. And this is a source of bromine radicals. And so whenever you see MBS, you want to think of allylic bromination. And then here, this is bromine. Bromine is a low bond dissociation. So, and same thing with this oxygen. These have low bond dissociation. So all you got to do is shine a little bit of, I think, blue light on it, and it easily breaks up this homolytic cleavage. This happens in the upper atmosphere, so you get a lot of free radical chemistry. So basically what happens is when you get this free radical, then it's going to abstract a hydrogen. So which hydrogen is it going to take in this case? it's going to take the tertiary hydrogen to generate a tertiary free radical, because those tertiary free radicals are going to be more stable than a secondary or primary, right? Just like the allylic one is very stable. And so that means the bond association to remove this hydrogen is going to be very low bond association energy. And so that is a way to just brominate an alkane. Now, I'm going to tell you something, folks. This is a big deal, okay? You need to start organizing your reactions on a reaction sheet for FGT. FGT is functional group transformations. Okay, so whenever you see me do that, I'm talking about a functional group transformation. When you change one functional group to another, you're changing an alkane to an alkyl halide. Now you all know lots of reactions where alkyl halides are your starting material, right? What mechanisms? You know an SN1, you know an SN2, you know an E1, and you know an E2. So you know a lot of reactions where the alkyl halide is your starting material. Now, this is the only reaction that you know that your starting material is an alkane, okay? See, these up here are alkenes. See, that's an alkene. This is an alkene. You've seen alkenes before. Alkenes undergo electrophilic addition. That's a functional group transformation from an alkene to an alkyl halide. Okay, you know that, electrophilic addition. This is an alkene to an alkyl halide. All right, but you don't know of any alkanes to an alkyl halide. You don't know of how to make any alkanes into anything. And in organic 1 and 2, it is the only reaction that can add functional groups onto an alkane. So that is an important reaction to remember for synthesis. Okay, so we're talking about Markovnikov versus anti-Markovnikov. And so it's very important that it's a different mechanism. This is anti-Markovnikov, okay, just HBr, and this is electrophilic addition. You need to know the mechanism. Notice I have a double-headed arrow because those two electrons here in this double bond are forming a new bond with the hydrogen. There it is. And then the other carbon, this carbon, gets a plus because it's formal charge now, and that's a carbocation. And that is a tertiary carbocation. So that gives you the Markovnikov regio selectivity. And then you have this bromide with its electrons, and it comes into that carbocation to make that new bond. See, double-headed arrow, heterolytic, and you make a tertiary alkyl halide. This is a primary alkyl halide, and it's an anti-mark, and that's because the mechanism is different. This ROR reacts with this to generate a Br radical. That Br radical now will add to that carbon, and you get a tertiary free radical. And this tertiary free radical is more stable than a secondary or primary. Notice the bromine adds first, and now you have to do a hydrogen abstraction. Notice I'm using fishhook arrows because that's the way free radicals are. This electron reacts with one of these electrons to make a carbon-hydrogen bond, and then you propagate. It's called propagation because it's like a chain reaction to generate more free radical. So the reaction can just keep on going. So they're different mechanisms. that is what you're seeing here. This is the mechanism in which I've been talking to you about. You see we have fishhook arrows. Those electrons are split homolytically. That means equal, okay? That means they each get the same, homolytic. And so you generate that. They're showing you that that's not that high. Delta H 151, that is a low bond energy. So we're talking, these are driven by bond dissociation energies. Now this free radical will take the hydrogen away. What's that bond, HBr? That is an exothermic reaction. This is an endothermic reaction. The bromine radical then will go and add to the alkene. So you have this electron and it will add to that carbon. These two electrons, one will go there to make that carbon-bromine bond, and the other one will go to this carbon to make the free radical. It is this free radical that is only seen. Okay, this is not formed. So the bromine adds to the least substituted alkene carbon, and the free radical then is on the tertiary because it's a lower energy intermediate. And so these are propagation steps. This is P1 and this is P2. In propagation steps, you always have to have on the reactant side, notice I said always, okay, so it's very important. I don't say always, always. Always on the reactant side, you better have a free radical plus a starting material reactant. Okay, that's how you know you're writing the mechanism correct. On the product, you better be getting a new free radical and often a product molecule. So here the bromine radical adds and you generate a free radical. That's why it propagates. You're going to copy this over, you see, in your mechanism. There you are. It's copied over. You react it with a new starting material, HBr, 3 fishhook arrows. Now you have your product and you generated a new free radical. Notice that these are exothermic reactions. This only happens with HBr, okay, and the free radical. No HI, no HF, and no HCl. HF is flammable and violent. It's too exothermic. HCl is too slow. No, it's just not. Yeah, it doesn't happen. HI, I think, just never happens. So you're only seeing this with HBr. Now this is a termination. You have lots of termination steps. A termination step requires 2 free radicals. They can come from anywhere. They can actually even be on the side of your flask, and they have to combine. Okay, and you see when they combine, they make a covalent bond, and then they shut the reaction off. Okay, so homolytic cleavage. You see these 2 electrons here, the fishhook, are being split into radicals. This is radical chemistry. It is not the 2 electrons, you see. It is a fishhook. And that shows the movement of 1 electron. Okay, what is the hybridization? Remember, hybridization means the shape. Hybridization is going to be an sp2. sp2, okay? So just like the carbocation is an sp2, so if it's sp2, right, you have an s, you have all the p's, right? You have 3 p's. Remember how we figure this out? So if you take 2 of the p's, well, that leaves you with 1 unhybridized p orbital. And that's unhybridized. And see, there's nothing in that when it's a carbocation. This is sp, this is carbon anion. This is sp3. So it's trigonal. sp3 is trigonal. We're not doing carbon anion. So anyway, I think the next slide will show you that your free radical will be like this, except you're going to end up having an electron in there. Yes, there. So it's trigonal planar, meaning it's flat. So everything bonded to that carbon is flat. It's in a plane. And then above it, you have this electron, and there'll be an unhybridized p orbital. Okay, stability pattern follows the same as the carbocation, and you get no rearrangements when you're taking free radicals. So there's no formal charge. They're all neutral, okay? There are no charges. So just like this, there's a formal charge. Well, you can do the formal charge of carbon. Group number 4 minus 0 dots minus 3 dashes. You can see that's a +1. If you have a carbon anion, okay, then you can see that that's -1. Well, free radicals, let's do it. Here's the carbon. Formal charge is group number 4 minus 1 dot minus 3 dashes, so it's 0. Tertiaries are more stable than secondary, more stable than primary, more stable than methyls. All right, so this is bond dissociation energies. You need to read about BDE, bond dissociation energies. You don't have to memorize them, but you do have to know which hydrogen gets abstracted in a molecule. You'll have to, and sometimes your ACS will ask you which hydrogen has the lowest bond dissociation energy. Okay, so I see that question often, so you are expected to know it. That means if you have this one, this would be a tertiary. You take that hydrogen away, then you're going to generate that free radical. You should know that a tertiary free radical is going to be more stable than a secondary, so therefore it'll have a lower bond dissociation energy. You see? So 381 is lower than 397, which is lower than 410, which is lower than 431. And so it follows the same pattern of stability. The reason why the allylic bond dissociation energy for that hydrogen is so low is because of resonance. Okay, so resonance, and that's the allylic position. So that hydrogen is, we might see it next slide. I'm guessing it's going to be around 360. Okay. This is benzylic, so you do want to be familiar with a benzylic hydrogen is going to have a low bond dissociation energy as well. This would be this one. The reason why is look at all of these resonance structures, okay? Remember, when the carbon free radical is formed, that's an sp2 carbon. sp2 carbons participate in resonance. Yeah, so here we are. I said it was 360, so 364 for this allylic position. Tertiary is 381. So see, this is actually more stable than a tertiary, and the benzylic is even lower bond dissociation energy than the allylic at 356 because of resonance. Now vinylic, no. These are vinyl. Okay, this is an sp2 carbon hydrogen bond. That is high. Okay, we kind of stay away from those. They don't seem to, that's a tough bond to break, 464. And like primaries aren't going to happen with 410. Allylic is 364. So, I mean, look, that's 100 kilojoules per mole. Okay, so whenever you get a plus and a minus, this is coming from an ionic reaction, and they're showing you that you have to be familiar with carbocation rearrangement. So remember, for my students from Organic 1, I say do the carbocation test whenever you generate a carbocation. So this is secondary. So you need to look at your two neighbors. If you traded places here, that would be primary. If you traded places here, it could be tertiary. So you're going to, in this case, you don't have a hydrogen, but you do have a methyl. And so this is a CH3 methyl shift, a 1,2 methyl shift. And so if you're going to do any kind of chemistry on this, you have to do this rearrangement where the positives now, the carbocation has moved to this carbon. That CH3 moved here. They traded places. This is a tertiary carbocation, which is more stable than the secondary. Free radicals will not rearrange. So when you do whatever reaction you're doing, in this case, if you had a BR, then it would not rearrange, and you could just go ahead and add that new bond there. So I do want you to be familiar with homolytic cleavage. This is going to be like the bromine. The X's, those are usually low bond dissociation energies. You're going to find these in the initiation, which we'll go over again in our next class time. Addition of the pi bond. This was happening for the anti-mark addition of HBr and ROR. Okay, so remember we added H to the pi bond. Hydrogen abstraction. This is for an allylic reaction, and also for, where you're doing just the making the alkyl halide from the alkane. So you're going to see that. And in a halogen abstraction, I'm not seeing any reactions where we actually are going over that. So, okay, so what is the product of the following? Draw the reaction mechanism on a piece of paper. So this is where I want to stop, and this is where I want to start the next time. So this is where we'll start on our class on Thursday, and I'll walk around the room and see your reaction mechanism. See if you can find it. You should have initiation step. You should have propagation steps. I think you'll have a P1 and a P2, and then you'll have a termination step. You will be abstracting a hydrogen on that first P1. So which carbon hydrogen has the lowest bond dissociation energy in this starting material? Okay, so you want to look at that. You could have a hydrogen here. You could have a hydrogen there. Have hydrogen there. Have hydrogen there. So you're going to the first propagation step, you will be extracting a hydrogen, and it will be the one with the lowest bond dissociation energy. So if you need to look in your book to figure out which hydrogen is going to be extracted in order to generate the free radical. And like I said, we'll start there. And welcome to organic chemistry.